record this one, and then okay, record the, I think it's recording. Okay, it's recording. It's recording. Give me 1 second. 2, 3. I'm sorry, my wife forgot my phone number. I had to write it down. Okay, anyhow, okay, I'm gonna go ahead and then share my other screen. Okay, so share the screen. I'm sorry. Before share, I have to open. Let's see. This one, we can a little bit talk about pretty much everything. So, do you see? Do you see this one? I don't think you see, no? I'm gonna just stop sharing and come back again. Okay. Yeah, now you can see. Yeah. I think you can see this one, no? Test for independence. Is that right? So I have several. Can you see? Can you guys see this screen? The other screen? I want to make sure because there are so many screens with me. I want to make sure that I'm on the.
Yes, we can see the screen.
With the normal plot, no? Plot from the regression graph?
Yes.
Yeah, good. Yes. Okay, I had to make sure because I have so many screens on my screen. Okay, anyhow, that what we were talking yesterday, pretty much several things, okay? Before that, we can go through the homework too, but these assumptions we were trying to, just I'm gonna go through a little bit today too. Residual was the, this assumption about this one. Those are the graphs that we're gonna see that when you run regression at the bottom of that, all the output. So normally you can see that the graph related to these to check these assumptions. Mainly that A, B, C, D. Here they say that that when it comes to here property, we were talking about 3 properties. They will always average 0 because the least square estimation procedure makes that happen. They will always average 0 because they were talking about the residual. Okay, we cannot check to see if the disturbance, we cannot check to see if the disturbance means the error behave correctly because they are unknown. Error is unknown. This is the key part. Okay, instead we work with their sample counterpart. As I mentioned that always, instead of looking into that error, you can look into the residual. They call this one residual. They call the E hat. Oh, I used to use this one epsilon for the population version, E for the sample version. That's nothing but the difference between your observed value and the estimated value. Observed value and estimated value. Down the road, you can see in the multiple regression, if you find the correlation between these two, that would be the R squared in multiple regression. We're going to get in over there too. So this is your observed value, whatever the being given in the data set, this is what you estimated. So there's a gap between those two because all the data points that you have evaluated not going to be on the regression line or regression plane or that regression hyperplane. So in that gap, always error has to be minimized. By minimizing the error, you can find something like this one. That's what they say. They will always average. Average means like an error. If you average error, if you take the sum, you don't have to even go to the error. If you sum up all the errors for all the data points, errors for all the data points, because those that particular summation would be 0. So that's why they say error is 3. Error will always have a 0 mean. Error has a 0 mean, or 0 average. And because the least square estimation, this is the procedure. We don't do that one. Okay, this is how you get the B0 and B1 through this procedure. This procedure works on if and only if your average is 0. That's how they say. B0 and B1, you get the values when B0, B1, B2, B3. Those are the regression coefficient values can be easily obtained because of that average is 0, the error average is 0. On the other hand, if the assumption A, B, and D of the section 2 are true, then residuals should be randomly distributed around their mean of 0. There should be no systematic pattern in the residual plot. See? There's no systematic pattern in the residual plot. That's how they say see? A, B, and D, except for this one, A, B, and D. A, B, and D. D. C for the normal assumptions. If you are checking for the independence, if you are checking for the homogeneity or heteroscedasticity or homoscedasticity, you can call that one any name. Or you're going to check for the linearity. See? Linearity. This is the linearity actually. Expect average disturbance EI to be 0. So the regression line passes through the average 0 means the linearity. That means your regression line becomes linear because of this reason. Okay. And that's why they say that there should be no systematic pattern. If assumption A through D hold, the residual should look like a random sample from a normal distribution. See? That's a third property. So mainly these three properties are already expanded within this one. Or on the other hand, these properties assumptions being condensed within these three properties. That's why they suggest these residual plots are important. Residual versus explanatory variable, residual versus predicted value. That means E versus X. This one E versus Y hat. For data collected over time or any other sequence, that means you have to have a time series plot or that sequence plot. Observation has been taken, how that has been taken, that order. See? Over time or in any other sequence for the residual in that. Always your residual is going to be on y-axis. Okay. And on the other hand, if you want to standardize residual, divide that residual by its own standard error. This will not change the pattern in the plot, but will affect the vertical scale. That's true. Standardized residual are always scaled so that the most are between -2 to +2. Why this going to be -2 to +2? Because that you can remember in that when we were talking about that normal distribution, we know that errors are normally distributed. Okay, that's the assumption. Errors are normally distributed. All the errors are normally distributed. So the error terms are normally distributed. If you look at their histogram, error term histogram. So this one, this is error. See, this is error. Or you can say error. I'm going to use epsilon or residual for E. Okay, doesn't matter. So in another way, epsilon hat TC, estimate of residual EC. Estimate of the error is this one. If you draw the histogram for that particular data, that data means for the residuals. See, it's always fitting into a smooth curve having a mean what? Mean 0 always. You know that. And its spread. So spread is nothing but standard deviation is given by sigma. Same variance for all error populations. Standard deviation SD. Oh, this, so, so they say here, if you want to standardize, so this distribution gonna go from, when you standardize, instead of this one, they say you can have Z standardized error, which is error divided by its standard deviation. See? So then you're going to have a 0 at the center again. And this time your standard deviation is 1 by standard. And this will going to be within 3 on this side, 3, 2, 1, negative 1, negative 2, negative 3. 3 on 1 above the mean, 3 below the mean. That's why, since we have a 3 to 3, but for practical purposes, they go from -2 to +2, the center. See? Those are the places where they believe that all the usual observations gonna observe, all the residual is gonna fall in -2 to +2. The rest gonna go to the tail, because that's the center of these two. It's a center between 1 and 3. See? The 1 and 3 center would be 2. Other than go to the extreme values, you can simply say practically everything gonna go -2 to +2. In such a scenario that you can truncate this one, data will be truncated. See? Then you're gonna work with only this part only. Let's say some student should be, some subject should be added to the survey or added to this our experiment when they are over 80, less than 65 or 60. See, up, this is called the left upright truncation. This is called the left truncation. Then you're going to work with only this data. And while they were in that particular day, that experiment, some people might gonna just leave the experiment. Then you're gonna have some kind of a missing data. That data should be tackled too. Okay. And if you are dealing with some kind of a survival analysis or some kind of a research related to biomedical research, their lifetime should be taken into account. If that's the case, that data we're going to call censored, because it has been censored here. We don't know how long that particular person going to exist until he's going to experience or demise. Okay, because of that reason that we have a censored data. So different kind of a data will be erupted. And in another scenario, what they're going to do for your understanding is that when they have like this in a certain experiment, they wait until that somebody first failure, like in the mass production of some electronics, electrical or mechanical components, the first failure. At the first failure, they're going to remove certain number of that they are components, products, who are at the threshold of failure. Then they go to the second one. They remove another certain number too. They go to another failure, third one. They remove certain number. Sometimes this number is fixed. They say, I'm gonna, every time there's a failure, I'm gonna remove 5 elements from this whole survey in order to make this one very efficient, convenient, and then for the less labor and then less cost. So sometimes they do randomly. See, randomly they remove. They first time 5 people, second time 10 people, third time maybe 2 people, like that. Those are called the random removals. Progressive. See? So there are so many kind of data. See? They were censored. See, you have taken out people who are at the threshold of a failure. They will be taken out. Then go to the next failure and then taken out another group. And we're going to do this one until we are done with all the subjects for certain given period of time. Based on that one, we have a type 1 or type 2 censoring. But anyhow, here that I'm trying to say that that's why this will be between plus and minus. We saw this one, see, residual versus this graph. See, they were see, how could we gonna see that it's gonna be, see, no particular pattern, see, same scatter, mean of 0, see, they were just spread out, like a, see, this way. See, there's no any particular pattern. So that means they satisfy that linearity, normality, that all kind of thing. Standardized residual and over time can do that. So here we mentioned that residual versus normal quantile. Residual versus quantile means like a how, what that means, the quantile. Quantile means how could they be gonna get the quantile? Is quantile. So they are getting quantile. It's Quantile is important because that you, in order to check whether these gonna fit in into the normal distribution, you check the quantile. Here residual is a predicted value. You know how to get the predictor. This is why you know predictor value. This is X. You know this residual is the order observation. How about the quantile? How they get the quantile? Because that when you have some kind of some data will be checked against another data set. When you have a two data set and then check against that another one. Mainly what we're gonna do, we're gonna get the residuals will be tested against the normal data, normal quantiles. There are normal quantiles, you know, as of now, standardized normal quantiles is nothing but -3 to +3. See? -3 to, these are called the quantiles. These are the quantiles. These are the standard normal quantiles. See, standard normal quantiles. We're going to talk about -3, -2, -1, 0, 1, 2, 3. And then see whether our residual, which we're going to go put into the y-axis, going to be coming from a normal distribution by looking at what? Quantile plot or probability plot. See, that's how they say normal quantile plot. See, residual. This is called the QQ plot, or sometimes called the PP plot, probability. What that means? That means you're gonna have this kind of a. See, this means you can get this. You can get the on the y-axis. You can get the empirical. Empirical means what? Empirical means practical. Practical means nothing but the observed, okay, or sample, coming from the sample, okay, quantile. Here you have the theoretical quantile. Theoretical means abstract quantile. Which are -3. Standardized. That means in our case, we're going to use the standardized normal quantile. Those are the values. Okay. -0, 1, 2, and 3. 3. In other quantile, how do you get the empirical quantile? In order to get the quantile, empirical side, how they get it? You don't have to do anything, but normally how they get it is like this. This is how they're going to get the quantile. What they're going to do, they're going to go over here, okay? We're going to see this is the probability, okay? This is the probability. I'm going to call this one empirical probability. You can calculate this probability, empirical, practical probability. I denote this by P. Here you have the first data point, second one, third one, fourth one, all the way up to N. And then observation. What are you gonna say? You say the probability, empirically, probability of getting first data point is nothing but 1 over N. You do the same thing for the second one. Nothing but 2 over N. So it's like a step function, see? In here, you have a 0, then you have nothing. Then open this one, then open here, close here, and keep going. And at the nth one, you're gonna go to the nth one, open, and go up, and go like this, N over N. See, step function. And if you go to third one, see, this is open, this location, 3 over N. Right there. It's for the step function. That's how you're gonna have something called the empirical CDF. This is called the empirical CDF. Empirical CDF. CDF stands for cumulative distribution function. See? Now what are you gonna do? You're gonna check it's, let's say that I'm gonna go to the ith one, okay? Ith one. See? Ith one, and I'm gonna check its corresponding probability. I'm gonna call that one PI. PI. here. Some people in our this one, see the way that they have done here to get the quantile they were talking about. Okay, we talk about this one. See, they use this one, this much. This is the quantile. I know it's not I over n. If it is I, it should be I over n my probability. See, my probability should be I over n. These are the probabilities. See? This is the second probability. This is the third probability. This is the ith probability. But that should be the n probability. See, En. En is n over n, which is 1. But Pi over I. But they have done some kind of a modification. They have done some kind of a modification. That modification, they have done that one in a several ways, not only one way. Because see, they have done this way. Not only that, if I show you something, I can connect this one. I can show. There are so many ways that they can do that one. See, this is the one we see over there. That's not the only way. Some people they have see it should have been I over n, but most of the practitioners they came up with a different formula. This is the one we have in our this here. That's the one we have right now for the probability. I minus 0.35 divided by n plus 0.25. Not only that, this has been, it should have been I over n. See, it's been, see, done in so many ways. These are empirical probability. So what are you gonna do? You get the probability. See, you get the probability and then probability, but I'm not gonna go to the probability, but from the probability, you go ahead and find its corresponding. If you know the probability, you can find its corresponding quantile. They come back again. See, come back again and see. They're gonna look for the what? Quantile. Standard quantile. Standard quantile. That's the quantile they're gonna use on this side. See this side. That's called the theoretical quantile. See? Sorry, that's the quantile they're going to use on this side. Quantile. Standardized quantile. Standardized quantile. I'm going to say steady quantile. This one theoretical quantile. Two in order to get the plot. If the plot, see, if you have something like this, that means normal. You can remember different shape will give you different type of distribution. But the standardized quantile, instead of that one, on what they have used just the standardized quantile, instead of that one, they use the residual on this side for their convenience. Sometimes you can use the residual only. Sometimes you can use the x, whatever the variable you are interested in on this side will be checked against the normal distribution. If they were coming from normal distribution, they fall into like this. See? All the data will be spread out like that. See? Okay, over here we have another one. This one you can see clearly. We were nicely put over here. Here you have the residual, okay? You have a quantile, the standardized residual. When you standardize the residual, they also gonna be between -3 to +3. This is the theoretical residual. Theoretical quantile. This is the theoretical quantile of residual, which are coming from normal distribution. This side you calculate. How did you calculate? You can remember that I was mentioning here. You don't do by hand. You look for the probability. From the probability, you go back. Okay, you go back and then find their quantile. How do you find the quantile? So if you go back to, this is how you're going to find the quantile. See, the TI, see, the corresponding, if I write this one, see, then corresponding, see, corresponding quantile, or quantiles for TI probability is, how do you find it? QI. Okay, quantile, I'm going to say QI for the ith one. So the QI, we know that TI is nothing but probability, the normal, standard normal distribution QI. So therefore QI is nothing but inverse normal in norms of what? That particular probability. That's how you're going to find the quantile. These are the QI come on this side. Okay? QI come on this side. And this side you have -3, -2, -1, 0, 1, 2, 3, 4. You are coming from normal distribution, standard normal distribution. So you're going to put into this one and see whether they will have a certain pattern or not. So these are called the empirical one. You calculate by hand. These are called the theoretical one, and see whether these quantiles are whether coming from this normal distribution. For the quantile, I'm using the residual quantile of residual. Okay, that everything has been done by the program. Okay, so if they were like this, see, it go down, negative skewed. See, if they go above this one, more often, that's a right skewed. And on the other hand, look at if they were equally distributed in the scatter plot, that would be normally distributed bell shape. If more on the above the line, more above the line means left skewed. More below the line means right skewed on the this particular scatter plot. This is a scatter plot. This is a scatter plot. This is the residual Q to Q, quantile to quantile. What quantile? Theoretical, sorry, empirical quantile to theoretical quantile. See, that's how they call theoretical. This side they should call the empirical quantile of residuals. Okay, we do everything for the residual. This is for residual, this graph for residual, this box plot for residual, box plot, residual, residuals, residuals. Okay, not for X or Y. Okay, we don't worry about that X or Y, that pair of data points, whether they have that. Can you remember when we did the regression, we were talking about the MPGCT versus engine size. We don't worry about that one. We get the MPGCT and its estimated value, MPGCT estimated value, and see how this point, let's say that for instance, that if you pick a 1 point here, how much away from this fitted line, that's the error. That error, if they were error being like this, you see more error, see? And that error being cancelled by the error to below the one. Look at here, more error. More error above means like a more error to this side. See, your tail is very thin. See, more error below the line. See, below the line. See, that means right skewed. So on the other hand, that way, or by looking at the QQ plot, you can figure out that one too. See, so those are the mainly major thing. Plus that one more thing I wanna show you, and then we can move on. This one. This one, sorry. The test for independence. Test for independence, you get the residual versus observation order. Look at the observation order. This is what they say. If you have a first data point, and second data point, third one, they're gonna fit into a certain pattern. Look at the pattern. Certain pattern. Okay. Look at here. Why they call the positive correlation. Okay, let's go to negative one. Here it's this one. See, this one suggests that the negative serial correlation among the error terms. Negative serial correlation exists when residual of one sign tend to be followed in time by residual of the opposite sign. What that means, look at the first one. First residual is below the average. Second one above the average. Below the average, above the average. Sorry, above the average. Below the average, above the average. below the average, above the average, below the average, above the average. See, like that. See, if they followed like that, see, negative serial correlation exists when the residual of one sign. Doesn't matter, it should go other way around. First above, positive, negative, residuals. Okay, I'm talking of positive or negative, positive, negative, positive, negative, or negative, positive, negative, positive. If that's the case, you have a negative serial correlation. See, that's how you're going to check the independence. There's no independence there. This one, they suggest that there's a positive correlation, as I said earlier, see, for positive, negative, see, and followed in terms by the same sign, see, same sign. They go by the same sign rather than going the alternating sign. If you have the same sign, look at that. See, below, 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 up to certain point. Then become above, see, yeah. Positive, positive, positive. First one, second one, see, second one, third one, fourth one, fifth one, sixth one. But here, see, look at here, see, the residual bounce randomly around the residual zero line as we hope so. In general, residual exhibiting normal random noise around the residual zero line suggests there's no serial correlation. Why we checking for the correlation? Correlation and independence go together, okay? If there's no correlation, they are independent. That's what I'm trying to say. This pattern, if you see this pattern or this pattern, they are correlated. There's no independent. They were dependent. Who we are talking about the dependent? The residuals, okay? Dependent. But independent when? The residual bounce randomly around this randomly. See? They were equally, see, go down, up, down, and then like this. Look at the pattern, this kind of pattern. Here, these ones and these ones are, see, kind of they get cancelled off. See? Look at these ones and these ones cancel off. Here, look at more positive than negative. Here, look at more negative than positive, like that. Okay, in another way. Or they followed one after the other as a sequence. If you're going to go ahead and check that order of the residual, first one, see, below, second one, see, above, below, above, below, like that. I'm not talking about everything, but that almost that majority of residuals, okay? But even the bounce in back and see around this residual equals zero, they cancel off, and then this is independent check like that. Rough idea, okay? That's rough idea enough for this class. So on the other hand, homogeneity, how do you check the homogeneity? In order to check the homogeneity, let's look at one more thing. See, look at it. Residual versus, let's say that you have here fitted value. If it is gonna go through a, see, funnel type, see, like a funnel, that means that the variance is getting increased, okay? So variance increased. So you can check this one with the aid of these plots that I'm talking about. See? Residual versus normal quantile. That means residual means theoretical quantile versus or residual. Even the residual, you can still use it, but most of the time they are using the residuals, standardized residuals, okay? Standardized residuals, the quantile, okay? Standardized residual versus normal quantile. How they calculate this one, I showed you how to get that. Standardized residual, okay? It's not about that simply that if you go to this graph, you can see clearly. Not this one. This one. This one. Okay. Quantiles. Quantiles. Standard. See, these are theoretical quantiles. These are quantile I created from my data. How did they did that one? By doing like this. See? Calculating quantile. They were not the, but remember, they were not the residual, observed residual. The observed residual we don't have here. We're not talking about the observed part. You might be thinking like, where is that the first residual, second residual, third residual? fourth one, fifth one, the nth residual. That's not what we were talking about. We're talking about how to get the CDA. This is called the probability related to the first one. If we have a first one related to that one, probability. That probability, and you can come back. But some people, they are convenient for this side. They use just the ordered residuals as well instead of quantile. Okay, you can do that one too. Ordered one. Some people use the standardized one. But okay, so many ways that you can get this done. But the standard way is to get the quantile, not the ordered, not the value. See, I don't have the value. I have location only. See, these are the locations. I'm treating to the location, not to the value. First location, second location, third location, fourth. They were equally spaced. When you have a, let's say that you have a first data point is 10, next data residual is 20, 30, then 60, then 100, then 150 like that. See, they were not equally spaced. I'm not talking about their values. I'm talking about the something called this, how to get the empirical probabilities. First location, second location, equally spaced third location, fourth location, get the stepwise step function. Then through that one, you get the probability. You come back and get its corresponding quantile and find its standard value. Okay. And they sometimes this quantile gonna be between the given two values. Okay, two values. Okay, two values. Okay, so there's a little bit. Maybe I don't want to get in over there. Simply you say that you have a quantile on this side, theoretical quantile, sorry, calculated quantile. Based on that one, you can figure out that whether this data, whether they are fitting into the normal distribution and normality assumption is satisfied or not. Okay. If you want to check the linearity as we did over here, you can check whether you have like a in this this graph. Okay, let's go to this graph. That's one or something like that. Okay, they were saying nicely distributed above and below the residual zero, then you don't have any pattern. That means that definitely you have equal variances and linearity gonna satisfy. If they will go like this, okay, that homogeneity, that means like heteroscedastic, that means unequal variances, like a funnel type. And if they have a pattern like this, see, some kind of pattern, you can fit into the non-linear. They don't linear. Okay, like that's only thing we can talk about that. But that's I think it's enough for our discussion. So we cannot go through in so much detail. Okay. So the next one we were talking about that including what regressive variable. Can you remember that we were talking about that one at a certain point? Sorry, the categorical regressive variable. The next one, categorical regressive variables were included. Get something here. Page 90, let's say 90. Should be. Okay, look like there should be another one. Let's take number 90. Number 90. This one, the principal component, first one, first page, if I can check it, it's easy. Don't have to write. Use the same thing. No, not this one. On this one, let's go to the beginning. Yeah, this the one. This one should be on this one. What happened? Like this, the book. I think something happened. Yeah, the pages. Let's see. Okay, stop from there. That's a 144 pages. lock this one. That's okay. We can just. Okay, so we were talking about that the indicator variable. Can you remember indicator variable the other time? So indicator variable, and this one we don't need, that's enough on this one. So on the seasonal effect, this one we were here. We included something, see, one thing is the two option first time, two option can be tackled with the one indicator variable or dummy variable. So in this example, see, employment about the, see the salary amount that education level, and this they were that drawn last time we did that one with respect to that gender, and later on we were just represented by we did this one in several ways. Can you remember? We represented this by some variable or the categorical variable. That's a categorical variable that can be denoted by another indicator variable or dummy variable. See? And we played with that one. Later on, what we did was we included three option one. You can remember when we fit into with the region, you cannot get any information from this guy. Only information if you fit in info region. See, we don't know if I'm interested in any south or west or midwest. You cannot get how much the sales would be for a given region. That's why you have to rewritten this one with the aid of dummy variables. See, that's what we did. They are the dummy variable. Either you can say x1 and x2. If you have a three option, you can go to two dummy variables, or they are on the levels can be utilized. See? Can try it like that. Or if you go further down, what's going to happen? Now you have to take into account something called the interaction. Interaction. See? Then here, see the location. See, now they're going to ask, is the location? Look at the question. Because the location is measured by two variables in a group, we need to do a partial F test. Look at it. The full model has the advanced, bonus, south and west, and the reduced model has only advertising and bonus with this one. How could you gonna see? Partial test has to be one. See what that means? See, you're gonna run with the not this one. Full model, southwest, see, full model. That means we want to see whether location is important. If you want to check whether the location is important, okay, you can get this done in two ways. Okay? But since we have fitting this model with the aid of this setting, two dummy variables. Look at the dummy variables. These two are the dummy variables, south and west, or x1 and x2. X1 and x2. These are the levels of that particular categorical variable. The variables levels, that particular categorical variables levels are utilized. If you have a three levels, you need only two levels because the other level has been set as a base. So with the aid of, if you do this one, now you want to see whether not the south or west, the region, overall region is important in explaining the sales. See, explaining the sales, but we fitted this one with the region as well too. So you can get this done in another way too. So you go to the region and you're going to check it's beta 1, beta node, beta 1, beta 2, beta 3. So beta 3 can be tested. Its estimate is 190. So once you run that one with this one, you should come up with this standard error. See? Standard error. Right? Standard error is how much? See? What happens if you just put it in the model? this region. R squared is 92%. You see, it's a very good. I think really good, more than almost 85. But error 6885. And standard error for the region. These are two different things. Okay, be careful. This is the standard deviation for the region. This is the standard deviation for the error. This is nothing but in ANOVA table mean squared error or root mean squared error, RMSE. That's that one. This is the one that we call it. But this one coming from a different place. That means like when you're gonna go ahead, that table I don't see over here. Okay. Let's see that whether this data set we can run on that SAS and this one. Let me see, Southwest. So we have chapter 7. Chapter 7 has this data. Sorry, chapter 7. Data Harris 7, I think. I said Harris 7 bonus. Male, female, not that one actually. This data set, no? Medical, see, region has been included, okay? See, look at this data. I'm gonna go ahead and give this data. Medical data. So in this data set, we have advertising bonus, see? Advertising bonus sales region being even included. Region has been given categorically 1, 2, 3, 1, 2, 3. Can you remember one is the Midwest, I think. First one, then second one, third one, West and South, like that. So this data, with that particular data, what we're gonna do, we're gonna see procedure. We're gonna run this regression. Okay, let's run regression and see what's gonna happen. These are the results. Okay, let's compare with our results. Okay, now the region has been included. Okay, so 84, 1.61, 1.1, and 180, 190. So this is the R squared is here. See, R squared here. See, that's for the overall. This is the ANOVA table. See, root mean squared error 68. This root mean squared error is nothing but the square root of this guy. Sum of squared error, SSE. Take the square root of SSE, become RN. I'm sorry, this one, mean squared error. Mean squared error, okay? Mean squared error. MSE. MSE, take the root on this one, square root. That is that. 68 times 68.88 means 4745.57. So if you take this value, root mean squared error is nothing but this guy. Standard error of the standard deviation of the error. What do you mean by standard deviation of the error? If you get all the data errors, if you're going to rank them, and then if you find that they are, you don't have to rank. If you find their standard deviation, that's that. Right? On the other hand, for the region, correspond to region, it has a standard error, which is 28. See, 28.69. See, that's the standard error for who? This standard error for the beta, if you write this on beta node, beta 1, beta 2, beta 3, then beta 3, sorry, 1, 2, 3, beta node, beta 1, beta 2, beta 3. Okay, the beta 3 is being estimated, which is called B3. Okay, B3. But B3 is not a fixed value. Even though you see under 19, we had this broader discussion. It's if you're gonna do this one again with the same number of data points, but with this, if you're gonna pick another sample from the same population and run this regression, you're not gonna get 119 for the B3. You get different values. Because of the randomness, that will have its own standard error. It will be fitted into distribution as well. We can remember that discussion. Okay, we did that discussion in broadly. So let's say that in this related to this one, this about B3, if I write that one. Okay, this one. So see, so they say the sales equals, okay, right here sales equals V naught, okay, I can write the original one, okay, expected value of sales, okay, that's how it should work. B naught plus B1 times advertising plus B2 times bonus plus B3 times region. That's your model, okay, that's your model. If you write just the sales with this one, sales only, you can write B naught plus B1 advertising plus B2 bonus B times, okay, plus B3 times region plus error, epsilon. But if you put the E, that's the estimator, that's the population version. This is the population. Those cannot be evaluated. B naught, you cannot calculate B naught. That's how you estimate. When you estimate, look at what do you have? Sales in sample version. It's in a sample, okay? This is in population. Sample you have, instead of B naught, beta naught B1 add plus B2 bonus plus B3 region plus residual. Or if you write without residual, you're going to put the hat. B naught, B1 hat, B2 bonus plus B3 region. Do you know all these values? Yes. B naught is how much? -84 plus B1 is how much? 1.55 advertising plus 1.11 bonus plus 119 times region. See? But we know that. See? Now, if you want to see whether the region is important in explaining the sales, you can at this stage, you can run the test for beta 3. That's what I'm trying to say. Beta 3 versus its counterpart, beta 3 not equals 0. In order to do that one, you definitely need what? Its corresponding t-value. That's the t-value you're going to see on this one. In order to do that one, you need what? You need the point estimate. You need B3. In order to run this test, you need the B3, not the beta 3. In order to run test, you need B3. You need its standard error. Why it's standard error? How come you have a standard error for that? What that means? That means B3 distributed according to a what? Normal distribution. I'm talking about B3. You see? B3. Out of all these, as I said earlier, if you repeatedly doing this experiment again and again, that B3. Okay? So the B3, whatever you see that B3, they believe, see, I'm going to call this one observed B3, which is 190. They believe going to go to the center of that distribution of B3. Not only this 119 we can have for this our whole, by any chance, if someone else has done this one and come up with the same the estimates, that estimate cannot be 190. It may be something else. That's why we're going to leave the space for them to add anything. We accommodate. See, they can accommodate easily. See, whatever the value comes, they can fit it into this distribution. See? But in our case, 119 is the absurd value. See? Not only that, this guy has his own spread too. See, I'm going to call that one, that's the spread of the B3, which is how much? It's already over here. See? Which is 28.68, 69, 28.69. 28.69. Standard deviation of B3. this one is nothing but mean of B3. Mean of B3. See, that's why now they need something called a T. T for B3. T for B3 is nothing but mean of B3 divided by standard deviation of B3. This is nothing but, see, B3, see? I'm going to say mu of B3. Mu of B3 divided by S of B3, which is 119 divided by 28.69. That's how they got this value. This is for all the parameters as well. They divide 190 with this one by this one. Then they got the 4.14. 4.14. 4.14. They believe this one fitting into not that distribution. That one also has another distribution. Look at what I'm going to do. T of B3 also distribute. You can draw the histogram for that guy too. See, that's a different distribution. Having the center 0, that means 0 for sure. This is called a T distribution. Then you go ahead and locate this one. I'm going to call the observed again. Observed, because based on your data. Observed. See? So you're going to go ahead and locate this 4.14 here. That's the observed T. B3. See, let's say this one. So what they say then, anything more than on this side and the other side, because we have to take into account the both sides, because it's a two-tailed test. Why two-tailed? Because of the not equal sign. Because of that one, I'm going to get that side. And there's another one I'm going to locate on this side, which is negative 4.14 on this side. And I say that anything fall on these tails more than 4.14 and negative 14 called the probability. So this part you can say probability T greater than 4.14. This part you can say probability T less than negative 4.14. The P value is nothing but the sum of those two, T greater than 4.14 plus probability T less than negative 4.14, which is we already found on this one. See, 0.0005. 0.0005. 0.005. Then by looking at this one, you can say since P value, which is 0.0005, is less than alpha, which is level of significance, which is 0.05, we reject H naught. We reject H naught and infer that region is important in explaining variation in sale. It's important according to this setting. But they say that instead of going to that one, they were thinking about now they have two of them. Instead of they designed this setup because of the categorical data, they included two dummy variables, which are called the south and west two dummy variables. Now you got the different variable that you run this one and you can run this one and then you can get that answer. Okay, again you have all the properties, you know. But in order to run that one, see, before you're going to run that one, you have to make sure you're going to set this up. You get the data and then set it back into that one, okay? So you're going to say my region, I'm going to keep the Midwest as my 0. See, look at the 0, both sides. 0, 0, 0. Region, 0. region 0. They all are zeros. And if you have a region 1, which is called the south, we change that one here. See? I'm sorry. Has that been changed at a certain point? Region. Yeah, whatever we call the region, see? Region 1 means south. Now I call the south, and which is 1. If region 2 is the west, region 3 is the midwest 0. Then you're going to run that one. See? You do this modification for that categorical or dummy variable. Sorry, the categorical variable being represented by 2 dummy variables. See? Look at. See? Now you come up with the south, midwest. See? So if you go to the region, see? You have a midwest, you have a west. Since the first guy in south, 0, 1, 0. Second guy in south, 0, 1, 0. 0, 1, 0. The third entry is in west, 0, 0, 1, like that. See? I added, see, this whole thing 0, this one is south. By looking at whatever, whenever you see the 1, 1 represent that particular sales are from south. This means that they are from west. This means that they were always midwest. How could we know the midwest one? You go this way. See, all zeros. See, midwest. All zeros. Midwest. 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 South. See, west. 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 Midwest. South. Like that. You can figure out. See? That's what we did. Then we're gonna run by introducing this new variable. See, I was introducing the dummy variable, which gonna take 1 and 0. Each one's gonna take 1 and 0. Okay? 1 and 0. That's the picture they were showing over here. Each one is taking 1 and 0. See? 2 options. 1 no 0. 1 no 0. 1 no 0 0. Each one. Okay? Then you're gonna run. Okay? Then again you're gonna see the result. Now we're gonna have a B1, B node, B1, see? B node, B node, B1, B2, B3, B4. Now you're gonna see that any region, see? Any region is important. You always have the T values and their corresponding values. Then you can look into the R square too. Overall checking you can do whether this is a good model or not. It looks like a very good model. See, R square is adjusted R square way high. Look at the root mean squared error. Error is minimized. Error gone down. 57 point something standard deviation. Spread of the error getting small and small. So that means that when you go over here, reduce, no, not that one. Sorry. See, in this case, now you have an issue. Now, if you want to talk about the region, which you cannot just standalone south and standalone west separately, you cannot talk about that. You have to take into account both. That's why you are using the partial test. See, you're gonna see whether the region is important in explaining the variation. We did that one earlier by fitting the data in a different way. Now we fitted the data by introducing a dummy variable. If the dummy variable still you have the same question, I want to know whether the regions is important. Which region you're gonna pick? South only? West only? No. You have to take into account both. If you take into account both, how could we gonna tackle? We don't have that kind of a test here to tackle both. Okay? You might be thinking one at a time and tackle. No, you cannot do like that. One after the other. No. See, it's an individual one. Whether south sales are important, whether the west sales are important in that one, or that increase or decrease, those things we can check that one. But overall, we want to see whether this question, answer to this question, same question we had earlier. See? This indicator you can here's what that one indicator variable. See, is location important? If the location is measured by 2 variables in a group, we need to do the partial partial error. Is location significant in explaining the sales? What we're gonna do, we run this way. We use this one. We did this one. We did this kind of a setup. So you know sum of squared error of the reduced model, which has like only just these two. These two only. Sales advertisement and this one. See? And then we can compare and contrast these two together and get the values and plug in into that one. See? So sum of squared error according to this formula, sum of squared error of the see this one with the sales model one. Model one means how many? All of them. It's a full model. Sum of squared error of the full model is 66414. So let's go down and sum of squared error of the reduced model. Sum of squared error of the reduced model is more than. That means like in a reduced model, the error left over is higher than in the full model. The full model, there's error being explained by each and every variable, but here more. 181176, 181176, and 66414. You saw that's in the full model. Full model. This one. When you have full model, less error, more error than a reduced model. And how many variables in the reduced model? Sorry, full model, 4. How many regressive variables in the full model? 4. How many regressive variables in the 2? And this is nothing but again that mean squared error of the full model. 17.3 and 17 from the 17.3, you should know how to find its corresponding what? P-value. How could you gonna find the p-value corresponding? See? What are you gonna do? You know that one. Now how are you gonna do? So we can remember that. See, we have a way to find that one. Go to one. Let's see, chapter 3. Here. You see, BFT T tabs, not this one. This one I'm talking about. See? Okay. Let's go to chapter 7 here. Paste it. I'm looking for p-value. I'm looking for p-value. I'm gonna add the f value. I need the degrees of freedom numerator. I need the degrees of freedom denominator. Okay, cards. Okay, no, this one and this one. So what would be the value? So can you remember? F value. F value. They're gonna do that one to the right, to the left answer, to the left. Not this one. 17.3. We calculated by here. It's not on any printout. Okay, 17.3. 17.3. 17.3. What's the degree for freedom of the numerator? Numerator degrees of freedom means the difference of these two, which is 2. Which is 2. Okay. It's 2. Okay, that's right. Then what's the degrees of freedom of the denominator? Second one, which is the degrees of freedom of the full model. What's the degrees of freedom of the full model? Can check on this one. 20. It's already there. 20. So if you run this one and print, you get a p-value. 0. That means you reject H node. What is your hypothesis? You didn't see the hypothesis yet. You didn't write the hypothesis. You didn't infer. So the second one, this is the one way of doing that one. See, it's a method 1. So the test for region, okay? Test for region. So method 2. Test for region. See? then you can say that you have full model. See? You know full model is nothing but you can write this time y. Okay, I'm gonna write with all the entries. Okay, data entries. So is that all the numbers? I can write with the numbers. Okay, it's easy. 435. See? 435 plus 1.37 advertising 0.975 bonus minus 258 south plus minus 210 west, right there. Then the reduced model when we run, we saw that reduced model we saw here. If you want, you can write it down. Reduced model. See? 7, this one comes up. This one. This one has B naught, see, negative 516 plus 2.47 advertising plus 1.86 bonus. So you have this one is the important one. H naught would be what? You're gonna say beta 3, no? Beta 2 equals to beta 3. 0 versus, I'm gonna say clearly here beta south, beta west, southwest versus HA means at least one pair, at least one pair. That means one pair means like a beta I. One pair not equal to this one. Look at how I'm writing. I not equal to J. Beta I or J. But I and J can assume what? Three things. South or west. Since in this one we have two, okay, we can just simply say that one pair, okay, this pair beta not equal to that one. See? But normally that when you have more than that, we can write see here they equal 0. At least, I'm sorry, at least not one pair, at least one of them. Let's try that one. One of them not equal to 0. So when you take that p-value, you say reject H naught. You reject H naught means what? This is how you set up. How you set up. Sorry, that's they say normal. That's the they haven't written here that. See? That's the way they have. See? They equal to 0. Those are not there, and at least one of them not gonna be 0. At least one region. See, so you reject this one. Since you were talking not only single one, two of them, you have to say at least one of them not equal to 0. At least who? Which one? You don't know. That part you have to check with another test. Since p-value, see, since p-value, see, since p-value is extremely small, we reject H naught. We reject H naught that see, beta south equals to beta west equals to 0. That one we reject. And we infer what? At least one of them not gonna be 0. Okay. And infer that at least and infer at least one of them equal to 0. Like that. Okay. That's what they were telling here. That's what they were telling here. So in addition to that one, now they are what they are trying to do. They were trying to introduce the interaction term. That means there might be some term, another type of variable used in the regression model is interaction. Sometimes there might be interaction between those two variables. See? Some two variables. See? Variable in the model, it means that the level x2 changes how x1 affects y1. With this variable in the model, it means the level of x2 changes how x1 x1 affects y. See, right there. So what they did was, see, what they did was, one of the two variables in binary, the interaction produces a model with two different slopes. Two different slopes. Look at beta naught, beta. So look at when this one, when x2 equals 1, when x2 equals 0, you have this one. When x2 equals 1, you have this one. What that means, see, look at with the two x variables, see, you have x variables, okay, beta naught, let's say you have a two variables, x1 and x2, and the third one would be the interaction of these two, third variable, see, and what they did was, they were combined. They absorb x1 from to here by factoring, see, beta 1 plus beta 3 x2 together. If then we can say when x2 equals 0, when x2 equals 0, you have this part. When x2 equals 1, you have this part. Look at what's going to happen. It depends on that. It depends on your. I'm talking about here the regressive. Sorry, the categorical variable. Categorical variable. This categorical variable. Let's say this is a categorical variable. He's the one playing a role here. See? X2 is assuming 0 and 1. Categorical variable. X variable, X1 already a quantitative variable. Let's say this guy is quantitative. This is quantitative. You're going to absorb, see, factor out X out to be get, see, different slope and relationships. Okay. So look at this one. Now what you're going to do? You think that a male and female for that one. Male and female, see, they have this equation. They have this equation even with the interaction. Look at here. This is the Harris Bank case. Suppose we suspected that the salary difference by gender change with different levels of education. We suspected that the salary difference is that. To investigate this, we create a new variable called this. See, we're going to create a new variable now and add it to the model. You have education. You have the gender. Now they say they suspect that the salary difference by gender, change with different levels of education. See, salary difference by gender gonna change with the different levels of education. See? Look at salary difference by gender. Gender already there. Okay, change with different levels of education. If that's the case, if you really want to know that whether the salary difference by gender change with the different levels of education. Now we suspect, we want to say that salary differences only for the gender. That part we check. You can check that salary are different for the, whether the salaries are different for the males and female by gender. Whether the salaries are different for the by gender, we check that one. We check that. Now we want to add another variable to that one. Education is a categorical variable, sorry, quantitative variable. We have in this, formula, we have what? We have the salaries. I think they call the salary, no? Salary, see? You have a salary, you have education, which is a quantitative, you have a males. Okay, males means a categorical one. We want to see whether the salary being, see, affected by this one, okay, that difference by the gender affected by that one, will be changed again with the level of education. Let's say different education level, same education level, sorry, with the given education level, we saw that with the gender, it's going to change. But with the different education level, how it's going to change? Is there any difference by gender? This one is the effect, this effect to that one. Not the same one, not the same level of education. Different levels of education, how it's going to affect to the sales. If the sales has been discussed by the gender, this is the what we are interested in, sales difference by gender. We did that one. For a given same education, salary difference by gender for the same education, we did that one. Now we want to see salary difference by gender with the aid of the different level of education. If that's the case, how you're going to enter this one? See? Their interaction terms, how they are interacted, should be added to our discussion. Then later on, for the males and females, you can get, see, this kind of a two different group for the, see how the interaction affected. So that's called the slope adjuster. See, can you remember in the very beginning I told you when I drew this graph, I had an interaction term. They came exactly like this. You can go back and see. It came exactly like this. It's for the Harris one, okay? Harris data. We can go back to that one. Can you remember we had this data? So, the education level, experience, month, and gender we were talking about, okay? And later on, see, we change that one, see, we change that one to like this, male, female, like that if you want. Get the gender new variable, okay, that's okay. Then what we did was that we drew that this one, see, this scatter plot with regression by gender. See, they had, this is how we're gonna get it. Now we can see that very evidently. Why we get that one now? In the beginning we didn't see. They gave in the beginning something like this. Can you remember for that one? See, parallel one. It's not the parallel salary. See, for the education. See, salary versus education for by gender. And our one came exactly like that, the way that we see over here right now. Why? Because it has an interaction term. Interaction term. Different slopes. Different slopes. Why different slopes? See? Different slopes. See? Look at the slope. Look at the slope. Look at the intercepts are different for sure, because you know that they're going to go and hit the y-axis at the different places. But in the beginning, it looks like they both have like the same slope. Means like their salary increment gonna be go based on the that education level, that with respect to the education would be the same earlier. But it looks like that's not the same. With respect to the education, they're different. See, there's the rate of change of salary with respect to the education. Or you can say that for that 1 year, the sales increment per 1 year experience, extra 1 year experience for male and female not going to be the same. Early it's the same. Why it's not same? Because there's an interaction term, because we were suspecting that, see, the salary difference by gender up to that point, again, will change with the different levels of education. with different levels of education, they change. They change. Look at them. Earlier, not like that. They both have the same the rate of change earlier in this case. If you go in the beginning, the way that they have, okay? Look at the 8 years experience, like the 8 years of education, males and females. That rate, not the, I'm not talking about that the salary differences. I'm talking about the rate of change. How their salaries are changed are the same. Rates are the change, same. If they have a one year more than experience for female and male, their salary gonna go up with the same rate. But still they have a discrepancy. It's being masked by the rate sometimes. They're gonna say, hey, for all of you that the salary rate would be the same. Then, but we know that for sure salaries are not the same. Yes, I see. They're different. But the rate, same. That's why they were thinking, we see, for the different levels, see, you go, keep going. See, you go to the next one. Still the slope, same. The 9 years. Same rate. 10 years. They go up with the same. For males and females with like a different salary scale, but the rate would be the same. That's why they were suspecting. Then it should be like this. If it's gonna come like that, means they're gonna go and cross each other. Means on this graph means like there's an interaction term. Interaction term has been taken into account already here when you prove that one. See, it's already embedded within that one. So here what they did was they calculated, and then in the SAS, it's already over there. Okay. If you run this regression and see what's going to happen. Run regression and see. You see anything here? 43, see 4173. 4173, 80, we don't have that one. See? Because this has been set up in a different way. With the interaction term being included. Okay? Even though on the graph it's been included, they have not taken into account the interaction term in these calculations. I don't see that one. See, I have two things, education and the males. Let's say that, okay, but we can do something like that. Here we don't see. In order for us to see, if you go ahead and put the males, okay, this for the males. Males, you are supposed to put the, sorry, females, if you put the 0 for this guy, okay, you're going to have 4173. See? 4173, and then education 1 going to be 80. See? You don't see that. And on the other hand, I'm going to put the males 1. Okay, that means this value would be added to this value, 4173. 691. You don't have that one either. See? Because the interaction term not being taken into account in this case, even though that the graph gonna come like that. See? When you do by hand, you can see clearly. See? This part not there. See? This part not there. MS slope. Let's try to get the MS slope and see what's gonna happen. Okay. Education means that one, salary. See, I'm gonna get this one. Not that one, sorry. And slope. Males. Do we have that one? Equation for the mixed model. The males. Owners, advertising. Yeah, see here again. I think I'm gonna get this one to the top. Okay. I'm gonna get this one cut and paste under the Harris data. Here means so education meaning education and men. Education men. Okay, this 101 for female men with the respect of that one you can write it. For that gender here scatter plot regression analysis of that one. Okay, good. Mixed model analysis of the mixed model, education and males. Is that the same thing? Data out Harris year B look like it's the same. Yeah. It's more or less. We don't need that one. Here we can. I'm going to introduce the educate times males. Okay, because the males has a numbers. Okay? Males have numbers. Okay, not the letters. We have to make sure you're gonna utilize the variable with numbers for the calculation. For the identification, you can go with the like a strings, but for the calculation, always make sure that pick that. If you don't see that one, you have to convert that to that numbers. Okay, that's another one too. So that one. See, you get this one. Okay. So go and put it back into that data set and it's load. Okay. Oops. MS load 0, 0, 0, 15. Say it depends on that what you have for that males and the males, and if it is female, that you know for sure you have 0, males you have 1. 1 should be multiplied by the education level. Okay, so that's the interaction term. Now interaction term has been thrown over here. Now you have a model salary equals see B0, B1, B2, B3. Okay. Would that be the same as what we see here? It's 43, 95, 62, see, 74, 73. Based on that one, see, based on that one, we wrote the equation. We wrote the equation based on B0, B1, B2, B3, B0, B1, B2, B3. Later on that, since this categorical variable or dummy variable, you can put 0 for the females and then reduce that one to education level, and then you're gonna have these two. The predict the sales or the salary for the anybody who for the male or female for that particular gender come up with a different education level, how much that would be seen. You can see very clearly. That difference you can see whether it's been affected or not. So now you can see whether this is going to be affect or not. What are you going to do? Affect or not? You have to run the test, no? That's what they say. So the slope adjusted implies the salary gap increases with the education. Slope adjusted implies the salary gap increases with the education. This effect is not really significant. The overall effect of gender is now contained in 2 variables. So the partial F-test would be needed to test for differences between male and female salaries. Okay. Look at, you go ahead and check this one. See, this p-value. This p-value means whether this interaction term is important or not. But what they say over here, see, look at what they say. Test in this particular, okay, this is the graph, you saw that one. Although the slope adjusted, they call the slope adjuster for this one. See, slope has been adjusted. See, to see the interaction effect. Once again, evaluate the equation for the 2 groups. The slope, see, not the same slope, not the same in the rate, different rates, different rates. See? Although the slope adjuster implies the salary gap increases with the education, salary gap increases with the salary gap. Salary gap increases. They both have a same, see, but it's been unfortunately, I don't know if it's a real data, it's very unfortunate situation because with the same experience, but look at there, getting that gap getting larger and larger and larger and larger. See? So that's why they say that even though implies the salary gap increases with the education, this effect is not really significant. It's not significant. See? Significant means that you're going to say that there's no, see, you're going to say that we don't not reject H naught. H naught means from which one? This guy we do not reject, see, 0.2. Don't reject. M slope, you're going to assume that M slope is 0. There's no such interaction term. 0. So then what they say, the overall effect of gender is now contained in two variables. Two variables. So partial F test would be needed to test for differences between male and female salaries. In a situation like this, see, you can remember when you're going to write that what they are trying to say, this one, this is what they were telling. This is the one that they were telling. See? If you have a like this, you have an interaction term like this. Interaction term is going to go and contain here, see, here and here. See, they were spread out. See, x2. Look at the x2. Your x2, which is that categorical variable, stay here and here. See? That's why, see. That's why you were trying to do a partial testing later on for the male and female. You have something like this. Then what? Then what are you gonna do? If there's any salary differences between the male and female, how could you gonna do that one? Which one you gonna take into account? Which one you gonna run? Can you run the whole thing? Can you run the whole thing? Okay. That's why they say you have to go to F test. How do you set up the F test? Okay. The overall effect of gender is now contained in two variables. Okay. Gender gonna go to two variables here and here like that. See? Gender here and here. See? Content. So earlier it's by itself because of this interaction term. Because of the interaction term, it's going to appear here and here, or here and here. That's the same thing I'm talking about. Here and here. So if it is here and here, if you reduce to this one, it's here and here. And if you reduce further down, you can get like this and this. Now this is for the males, females, this is for the males. How are you going to check the interaction term? That whether that the salary difference by gender has been influenced by the education. Influenced by the education. That's the question we had, no? We had that question. Interaction term question. Salary difference by gender has changed with different levels of education or not. Because of that one, you have to run the F test for that one. Okay. So I'm not going to go to that one. Gives like a rough idea. Okay. For you need the rough ideas for what, because these are very broad, very heavy area. Because within this short period of time, we cannot go through all these detail that much. But we try to do our best. Okay. Okay. Then what? Then that's mainly that this is how you're going to tackle that one. So related to, as we say that with the, in the homework 3, So that we did that one up to a certain point because we have a homework 3. Let's see, look at the homework 3, what it's talking about. See, homework 3. See. You may use the data either slit study data, okay, the following instructions, slit log, see, wages clean, see, the slit data from the has the 7,425 rows and 5 columns. The data from 1994 Web of Canadian Survey of Labor Income Dynamics for the province of Ontario. There are data, particularly for wages, but they have been clean. Okay, these are clean data. That's why they say clean. We don't have to clean, but our data set slit log wages clean.csv clean slit data with log wages or data imported from slit blah blah blah, which consists of 3,900 out of 7,424. Now we have reduced that one to 3,987 entries. Does not contain any missing entries for wages or any of the other 4 variables. So you don't have to clean them up. You don't have to do the imputation. So wages, education, age, gender, language. Those are the ones. Create a scatter plot matrix for the continuous variable on wages, log wages, education, and age. Wages and log wages, have they been given on the data set? Log wages, we have to check and see that whether they were given. Log wages have been given. I'm going to go ahead and pull that out. Number 3. Yeah, log wages, see, you don't have to give the log wages, see, it's been given. In our data set, in the original data set, there's no such thing. This log being created and put it into our data. Language, categorical, 6 categorical, 2 categorical variables. This one has a 2 levels. You need only 1 dummy variable. Here 3, English, French, and others. Therefore, you can easily use 2. 1 less than the number of levels. That means 2 dummy variables. These are age and education level, and the wages and log wages, they all are given in numeric. Okay. So they will ask us to do wages, log wages, education, and age. Just create a scatter plot as usual. It's easy. Okay. So let's go ahead and get this data. Okay, data out. Anywhere, wherever they go. Okay. We're going to go to the work directory. Okay. Oh no, data out, sorry. It's going to go to data out directory. Then so then we can, those we can do. Wages versus log wages versus education, and age, something like this. You can, it's like a clusters, see, not even clear. That's why sometimes transformations are important. Number 2, what they were looking for. See, created 2 groups, scatter plot for wages and education. One for using sex as a label for variable, and the other as using the language as a label for variable. So create 2 groups scatter plot. 2 groups scatter plot. See? That means they've been grouped by, you're going to use the scatter plot between wages and education. These 2 should be grouped by, first one is by the gender, the other one should by the language. Okay, that's what they say. Okay, be very careful. These are the 2 variables should be in the scatter plot. It's a scatter plot, okay, not a scatter matrix. Okay, these 2 only, wages versus education, but it has been grouped by gender as well as language. Okay, see, so scatter plot, wages and education grouped by gender, and regression line has been drawn for that one in a similar fashion. Wages and education grouped by language. Okay, see, all these we can run at the same time. Scatter plot of wages versus education by gender. Okay. By education, language, English, French, other. Okay. And the number 3, what they will look at. Number 3, they want to create a regression model using wages as the dependent variable and education and age as the independent variables. Okay. Age as a dependent, education, and both are numeric. Okay. Just run the regression. That's what they say. Run regression. And the variable they generate there. Now, whatever describing overall performance is the model is a good fit, explain using hypothesis testing, F-test, plot generated by SAS. You can utilize everything now. As of now, you can talk about the overall fitting by looking at this one. Individual fitting by looking at this one. And by looking at the graph, this residual, normally assumption being satisfied. Those things you can discuss. And quantile, see, normality assumption, again, satisfied to certain. And residual versus the predicted value. See, look at here. I see residual versus predicted value, see, like a funnel type, see. That means that homoscedasticity being violated is a heteroscedastic, see, look at, like a funnel type. You can discuss those things too, mainly this one. If you want individually their graph, we talk about that one yesterday too. Individually, you can get those too. But anyhow, from this one, you can get the help and then make conclusions. And you can talk about, see, look at the R squared, extremely weak, 24% of the error carried from the empty model being explained by this model. And the root mean square is here, see. So much of it carried, this much being only explained by the model. Model is a weak model. Those things you can discuss. And number 4, create a regression model using now log wages. Instead of wages, log wages, number 4. Okay. Pretty much very straightforward. You don't have to worry about anything. Okay. This one is look like, okay, see, when you put the log, see, they were equally spread out. The funnel type gone. Equal variances, unequal variance problem can be handled or remedied by taking the log, okay? By taking log. That can be tackled by taking logs, okay? Taking logs. And what else? We can talk about so many things we can talk about. Okay. And we're going to talk about later on these two. Are they correlated? Are they correlated? That's correlation called the Marticoli rate. See, are they correlated? Why they were correlated with this guy? See, this is a regular correlation. Regular correlation. Those are the correlation you saw in that matrix. Scatter plot. And based on the ANOVA table and everything, you can talk about that. Now what? Now in number 5, say using the grouping variable for sex and language and add to this model. Select the grouping variable that creates the best model. See? Okay, now we're gonna group. We need the numbers for this to run. We cannot run without the numbers. See, male and female. We have a male and female. I'm gonna give another name for sex, converted into gender and give 0 and 1. And languages, English, French, and other, those things. Language has been called now language reg. That's a new variable. And convert like this. Okay. And then we're gonna run. Okay. We're gonna add that edge, gender, and that one. Sorry, gender. So here, see. Okay, at this point, see. we can intensive, what do you have here? Tesla. Oops. Hold on. I think so even though that we have to cover that ANOVA analysis of variance this week, I don't think that it's important. We can cover next week because the thing is, and we can, if time permits, we can cover tomorrow too. But mainly for the homework 3, we don't need that. Mainly we have to cover the variable selection procedures. Language rate, gender, log wages, language, gender. Look at everything being that spread out like this way. See, women and men. See, you can easily identify because that's the way we have. So this is our variable. Yes, see, see, language rate, gender. Within the language range, now we're gonna call the same women and men, but start still running, still running. Yeah. And yeah, we get the women and men. If we do that kind of adjustment at a certain point, yeah, they get the women and men. We do that one early somewhere. The 6 has been converted into gender. Okay, that's okay. See, 6 to gender, language to language range, language to language range. See, 0 to 1, that one. Where this 3 languages, French, English, and other, okay. Within this women and men, are they called the women and men within the data set? Wanna see? But they call the female and male. Where, how come all of a sudden they convert into, did we change it? Yeah, see, because we have done this one early, it's already over there. That's the problem. So all possible model is mainly, let's see why we really need to gender. Okay, what we're gonna do that the gender we're gonna write in terms of women and men. That's, can you remember that in order to write that the equation in terms of the categorical variable, dummy variable, see, these are the dummy variable, that's a different discussion. But here simply we say that add these two to the, there are 2 steps, okay, here 2 steps. I really want to add these 2 to my regression calculation. I cannot do the regression calculation, they keep as like this. What I did was I assigned the numbers for them, 0, 1, 2. Okay, 0, 1, 2. And then I simply call the new variable gender, and then they have a numbers now. Instead of male and female, they have a numbers. Then I later on what I'm gonna do at another step, I'm gonna change the gender to men and women. And the language too, French, others, and blah, blah, like that. Then I'm going to introduce the dummy variable. Dummy variable has not yet been introduced. Only thing what I did was I was just simply convert them to the numeric. That's it. Convert them to numeric. Categorical, these are strings, or that qualitative or categorical to numeric. That's all I did. I put as it is. And then I ran. And when they say, then run the regression. I can run regression as it is. See? And is there the same thing here? I'm going to see why the other two. Regression model. Okay, these are wages and these are log wages. That's okay. See, this one, I did that one for wages as well as log wages, but they don't ask that one. No, do they ask? Number 5. We are on number 5. This one is a very serious issue that we should not have done because so much data. Stop. Come on. Okay, number 4 says the log wages versus education and age only. Log wages. I did this one even for the wages too. The pages and come back again. Yeah, use grouping variable for sex and language. Add these to the model. Select the grouping variable that creates the best model. That's number 5. Yeah, number 5. So we added this one to here. See, and I did that one with respect to log wages as well. Now what? Now here, see, regression with the aid of the gender, female column. See, I can run the regression. See, same thing I had over there. Okay, what I'm gonna do, I'm gonna get these two and then copy and paste here. If you want, you can run like that way too. Okay, here. See, right after this one, before we come to all possible methods, get this one this way. See, instead of writing this one at a time, gender and language rank. Okay, or the language. I'm gonna go to gender. There are levels being utilized as like a dummy variable. See, dummies. In order to convert them to dummies, this is a procedure. See, 0, 1, 0, 0. For the men are zeros. The other one is 0, 1. In a pretty much similar fashion, the base should be what then in this case? The base is men. Okay, men is the base. Okay. Here, see, language rate again converted to French and English, French, English, others, and French, English. Then our other language has been kept as the base. Okay. So now I'm going to run the regression like this way. So after doing this one, see, because I express, if you want, you can do that way too. Data out is not assigned. Let me see what that means. Data out. Oh yeah, we just started. We go over here. First, we're gonna run this one. We have to do that one. First, changing that one to giving numeric values. at that stage, okay, that stage I'm giving the numeric values. Run is came to okay. Okay. Men and women, French others, language reg. Okay. Then let's count this one. Sorry, they are look like and I'm gonna get this regression done using the category, the dummy variables. Men or women would be my dummy variable. In the other case, my French or English or others, but in my case that I got the other would be the base and the rest other dummy variable. They're not going to even ask about any interaction. Men would be the that base and French, English separate. You can do that one. If you want to know, if you want to see that whether the language can affect to the salary, then you can have to do the what with the. If you're gonna go ahead and do with this one, you have to do the partial test. This one also partial test, but you don't need the partial test since that we have on one variable. By looking at simply that its own the p-value, you can decide whether that this one is playing a heavy role. But the partial test would be more solid and concrete. Okay. Okay. Now they were asking about that use a grouping variable section at the distro. Select the grouping variable that creates the best model. Explain the performance. How do you create the best model? Best model, we're gonna do the theory tomorrow, but for time being, like you can see that there are several ways you can look into the best model. How do you figure out the best model? See? Best model. That means in order to get the best model, we'll go to the variable selection procedures. See? Under that one, see? Variable selection. See? Previously, we discussed some test, t-test, partial test. That partial test, t-test, overall test, there are 3 tests we did. Help us determine whether the certain variable should be in the regression or not. We did that one. Here we look at several variable selection strategies that depend on the idea. Okay. We look at several variable selection strategies. In this section, strategies, several variable selection strategies. If an important variable is omitted, look at what can happen. The estimated regression coefficient can become biased, systematically too high or low. Their standard errors can become inflated, leading to imprecise intervals and poor power in the hypothesis testing. So sometimes due to this by accident, because of these tests, with the aid of these tests, if you are planning to keep certain variables or remove certain variables, sometimes very important variables will be removed. See, that has to be that thwarted. I mean, they stop that one. See, an important variable is omitted, the estimated regression coefficient can become biased. On the other hand, their standard errors can become inflated, getting into imprecise interval and poor power. To prevent that one, they were looking for the strategies. Compute a procedure that briefly examine every possible combination of X and report summaries of the fit ability, rather than just go to that 3 overall, the 3 tests that we were talking about, overall, partial, individual test. Now we're gonna come up with a very powerful selection algorithm. These are for deciding when to drop or add the variable. We decide perfectly when to add, when to drop variable. It's called the backward elimination, forward selection, stepwise regression. Okay. See, all possible regression. See. Sure, thank you very much. Yeah, thank you. Sure, tomorrow. Yeah, see you tomorrow. I keep going on this one. Okay, thank you. Good night. Yeah. Yeah, so see, then in this one, all possible regression. Look at here. before you're gonna see. On the other hand, non-guarantee you can get the see non-guarantee you get the right model because they do not check the assumptions or search for the omitted factor like curvature. None have the ability to use the researcher's knowledge about the business or economic situation being analyzed. So that means these methods even so sometimes scrutinize. I mean, like they were said as a non-guarantee you get the right model because they do not see check the assumption. Which assumptions? Can you remember the error assumptions are not checked by these procedures. But when you go to these tests, why we are going to t-test, partial test F and the overall F. During that time, by looking at all the graph, come along with this one when we're going to run the regression. Can you remember when you run regression, you get the t-test results, not the partial test results, but some components that are really needed to be evaluated at the partial F come along with that regression output, plus the overall F test. Our information now come along with that output. But here not like that. In these methods, we have a serious issue. The assumptions are not checked. Okay? And assumptions are search for the omitted factors like curvature. They don't check. None. See, none have the ability to use the researcher's knowledge based on in the context of the business or economic situation. Those things, that kind of a situation. That how they're going to do that one, people don't know sometimes that in mathematics or that in one biological researchers might going to think that some one variable is not important to explain some kind of a regression, some kind of a response, not be taken as a like an unimportant variable by the people who are in business research or economic research. So that's why it depends on that situation. So that's why they keep going and looking into the different format and try to come up with all possible regression in the beginning. If there are k many variables, k x variable, okay, k many x variable to consider using, there are k squared. Let's say I have a 5 variable, I have a 25 variable equations to be considered. See? There are 25 regression equations. Obtaining these, see, sounds like a ton of work, but program like SAS or Minitab have algorithm that can measure fit without really producing the equation. Okay? They do that one right away. In all possible equation, in all possible one, what they check? They check R squared, all the way, see, all possible regressions. They say here, okay, they say here, look at. There are, if you have X variable, there are 25 variables. Let's say that in this example, how many variables? 1, 2, 3, 4. Then how many options do we have? 4 times 4, 16. Let's say 16. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15. You are missing one. Yes, you know what is missing. That's called the null model. Without B not only. B not only. Here B not and B1 for the first one. Can you remember? That one is the 16th one. All the time that one not important, so we're gonna just disregard that one. This is 16. On the other hand, and how many options, how many regression models do we have with the single ones? The doubles, triples, 4 that see these are called that queen, not the queen, chordables, or that 4 variables, all the 4 variables. See? We can check that one too. So this is like a, see, here we have one at a time. See, we have a 4 variables. Out of 4 variables, you're gonna pick one. That's called the 4 choose 1. 4 choose 1 is 4. You know that one. We can show that one later. And this one, you have 4 variables. Out of 4 variables, you're gonna take the 2 at a time. Then 4 choose 2 is nothing. How much? This is 6. Again, 3 of them. 4 choose 3 at a time. See, which 3 we don't know. We can go with the 3. That's called the 4 choose 3. 4 choose 3 is same as 4 choose 1. So that's why you have a 4. 1, 2, 3, 4. And the other one is 4 choose 4. Out of 4, You're gonna pick all of 4. 4 choose 4 is always 1. I'm gonna write that one. I was just telling here that when you have all possible variables, if it is 4 variables, 16. If you have 5 variables, 25 option. Even with that one, again, you can break down and see that how many variables, the regression model, how many regression model can be created with the aid of singles, doubles, triples, and then so on. Okay. That part we can tackle too. And in that one, what are you going to check? R squared adjusted, something called the CP, see? Mallows statistics. This is called the Mallows statistics, CP, and standard error. Can we get those? Yes, we can get those easily. See? Okay. I'm gonna write over here. Okay, see? You go to the model, education, age, gender, language rate, and then you're gonna put your option, selection. R squared, it's called R squared, adjusted R, you call H R squared, CP, R, SC means root means squared error. See? Everything you can easily get. All possible, all possible models will be listed here. See? Look at, as I said, see, these are singles with the 2 of them, with 2, with 3, with 4. That's the same picture that we're gonna see here. Sorry, this one. Advertisement, advertising, bonus, competition, market share. So the same thing. R squared. So the same example. No. This is different example. Okay, this is for the homework. Let's go to chapter 7. Chapter 7, I can do the same thing for chapter 7. You can see men and women. This is for the market share. That one, if you see the for the same thing, let me see. Oh no, chapter 8. No, chapter 8. Stepwise, all possible. We're gonna do this one tomorrow, but for time being, let me see. Okay, first get the data set. That's the same Medicorp data set. Okay, I'm trying to get the same thing that here for you to see too. So Medicorp data, this is chapter 8, not in homework. Homework, we have a similar one, okay? Bonus, market share, competition, and region. Region has not been taken into account. So they go the advertising, bonus, market share, and competition. And we're gonna look into some kind of a statistics. What are the statistics? R squared, adjusted R squared, something called the CP, the Mallows statistics. We're gonna do all details tomorrow. Now, if you run this one, all possible ones, it's gonna show nicely. So I think, you see, you go over there and then go to selection and get that one. It's gonna show, see, exactly the way that we have over here. R squared, 0.8106, 8106. Adjusted one. This one, CP, root mean square. Okay. Now, we have to look into few things, but more detail we do tomorrow. But we have to look into one thing that I was talking about. Okay, I had to show you this one. In that particular example, K means number of regressive variables. Sorry. So we can pretty soon we can stop. Okay, and number of regressive variables, variables, K equals number of regressive variables, which is 4 in our case. Then you know total number of, therefore, total number of subsets or regression model would be k squared, which is 4 squared, which is 16. Okay, 16, which should be k squared. That's what they say. And the first model should be what? Y equals b naught. Next one would be what? B naught plus B1 add. Okay, one at a time. And the second one, y b naught plus b1, another type of b1. Okay, not the same b1, even though I put, that's why I'm going to put b add times add. So that's okay. I'm going to put the b1 for my convenience. It's not a big deal. You know, they're different when it comes to the other one. This one b1 add, the other one b1 a bonus. Okay, the other one b naught plus b1. You could do all that possible ones with the singles marker chair. The other one is b naught plus b1 competition compete. See? You see that there are only 4 for this category for singles. See? The single. See? This is 0 1. See? This is the empty model. You know that empty model. See? See? It's a bivariate model. Bivariate model. One variable only. One regressive variable at a time. Bivariate models. How do you figure out that and how many of them? You can simply say out of 4, we have 4. I'm going to choose choose 2. See, 4 times 4 combination 2. Out of 4, you're going to form models. How many models? How many subsets you can pick from the 4? If you have a 4 element, like if you form in a committee, if you have a 4 people, how many committees can you form with the aid of the 4 people? 4 choose 2. So you can simply simplify this one shortcut 4 times 3. Okay. I'm sorry, 4 choose 1. Why I'm looking at the wrong one. Okay, 4 choose 1. I'm sorry, 4 choose 1. One variable. 4 choose 1 is nothing but 4 always. 4 choose 1. So called 4 choose 1 equals 4. This is the notation. If you want. 4 choose 1 is 4. See? 4. That's why 4 options. And in the similar fashion, the next set, you have a 2. Okay? 2 variable set. How do you do that one? 4 choose 2. You have this notation or this notation. 4 choose 2 means you're going to 2 times 1 here. Same number of elements you're going to put on the top. And you get cancel of 12 divided by this one, 6 options. Then 3 variables. 3 variables. You have 4 choose. Okay, I prefer to use this notation. 4 choose 3 is same as 4 choose 4 minus 3, which is 4 choose 1, which is 4. The last one, 4 variables. How many submodels for 4 variables? 4 choose 4 is always 1. See, that's how you're going to see all these options. Okay. So, see, that's how you're going to see. For there, we're going to looking into R squared adjusted, and CP. CP is what? CP, normally CP is some kind of a parameter. CP, they think, okay, CP, we talk about, do they have CP here? Let me see CP. Let's have a like that. Stepwise selection procedures, not guarantee, okay. Keep going up CP. This model CP. Yeah, CP here. There you go. See, that's the statistics, CP statistics. SSE of the partial model should be divided by the mean squared error of that. Means partial means if you are here. Okay, if you are here, let's say I'm gonna see. Let's say you are here. That's the partial one. You're gonna go to the, it's what? It's sum of squared error. You can find sum of squared error because you can run that regression. Let's say advertising and competition, sum of squared error. Sum of squared error, you can get by running regression on this one. You get the sum of squared error of that one should be divided by the sum of mean squared error of the full model. Full model is the last one. See, that's the full model. You can run this one too. Get the ANOVA table, you can get the mean squared error. That ratio and subtract the n minus p. P is the what? Number of variables in the what? Is the number of p variables in that particular partial one. Okay, p stands for partial law in that particular one. In this one, not the full model. In the model that I was talking about, advertising and competition, how many variables to be estimated? B naught, B naught, B1, B2. Right there. That's the formula. So that's the CP formula. That's called the Mallows statistics. See? CP. CP means Mallows statistics. Given by sum of squared, this one of that particular model, divided by sum of squared, mean squared error, sum of squared error. Sum of squared error of that particular model divided by the mean squared error of the full model. Okay, full. Okay, minus n minus 2p is the number of parameters. Meters in the reduced model. See, they say that if you draw this one versus P, CP versus P, see, the graph is like something like this, but it's gonna be straight line. It's gonna be straight line. See, that's what they say here, CP. Theory say that in a model with the bias, CP will be large. If it also say that in a model with no bias, CP should be equal to P. If there's no bias, CP should be equal to P. It can equal to P only if they were fallen into the what? Straight line only. CP equals P because if it's going to go through this origin, this straight line. Okay. If thus recommended that we consider model with the small CP and those with the CP near P. See? We have a small CP. Okay. See, small CP. When you have a small CP, see, you have a small CP. See, small CP means what? They are corresponding P. That means small p. See, see, small p. We'll have what? See, CP. This one is Mallows statistics versus how many variables in the, how many parameters to be estimated is the one that we're going to take into account. See, number of parameters. Number of parameters. Okay. Number of parameters. So here CP equals to P. See, CP equals to P. See? That's the one that they're gonna take into account. That's why they say that CP. We're gonna do that one in detail tomorrow. Okay, for time being. So have a look at this one, and then out of that one, we go to the selection procedures. Very easy. We don't do anything by hand. We just go to the regression model. I have given this for the example. You pick the selection model. See, model, go to the selection, the forward door, backward door, stepwise. And you're gonna put here SL stay. Stay means like a significance level to stay. Significance level to entry. Enter into that one, you really you have to give the significance level 0.05. Or you have to take it out, you have to give that one. and based on the which procedure that you're going to utilize. That's a different setup. Here, how could you going to pick the best one? By looking at, okay, I do that one and we can stop. By looking at related to this example, we're going to go through them again later tomorrow. What is this? Right here. So we picked in this one by looking at all these procedures. We pick the one with the best model, the two variable model with the advertising and bonus and the smallest CP. When the CP is small, smaller CP, see? Smaller CP, highest R square, smaller CP, highest R square, highest R adjusted, and the smallest SC. This would be the best model. And then there are some other two models gonna go very close to that one too. They can be recommended too, but look at smallest, highest. That's the model we're gonna take into account as the best model. When it's not even enough for you to come up with the best model, you're gonna run that selection procedures, okay, and then see whether it will be convinced or not. See, again, you're gonna run that one and see whether you say, let's run this one more. This procedure called GLM select procedure. Okay, again, see, advertising and bonus will be given by that procedure too. See, step-by procedure. That gonna give the same thing that we got it from that other procedure. They were convinced. Okay. So what I'm gonna do, I'm gonna just a little bit stop over here. We continue this discussion and then finish the homework and then finish these procedures and then planning to go to that analysis of variance next week because it's not in our homework. Okay. So we can take time and go through that everything again and again and then until you guys can get convinced. Okay. So if you don't have any, do you have any questions? Anything you want to discuss? Not. Okay. I'm planning to stop over here. Okay. And have a good night and see you tomorrow. And then we'll continue this discussion and stay safe and be well. Okay. See you tomorrow. Okay. Take care. Bye-bye.